Hello, my name is Carson Drummond and I'm a graduate student at University of Central Florida. Today I'll be presenting a literature review on modern rocket engine cooling techniques. This topic is central to propulsion engineering because rocket engines operate in extremely high temperature and high pressure environments where material failure is a constant risk. The ability to manage heat effectively is directly connected to engine reliability, performance, and allowable burn time. My goal in this talk is to summarize 5 technical studies that examine different cooling approaches, identify the advantages and limitations of each method, and highlight common trends across current research. To give some background, cooling strategies in liquid rocket engines generally fall into 2 major groups, those being film cooling and regenerative or cooling channels. For film cooling, this is where a thin layer of fluid, which is often a small proportion of the propellant, is injected along the chamber wall to protect it from direct exposure to the combustion gases. While this method is effective, it can be challenging to implement because it requires very precise injector designs and often reduces combustion performance due to flow dilation. The second major approach is regenerative cooling or cooling channels, which relies on propellant routed through channels built into the chamber and or nozzle walls. As the coolant absorbs the heat, it lowers the metal temperature, which then preheats the propellant for combustion. This technique is widely used and highly efficient, but the design and manufacturing of cooling channels is a significant engineering challenge. These 2 categories provide the foundation for many of the papers that I will be discussing next. The first study we're going to look at investigates regenerative cooling in a nuclear thermal rocket nozzle, which uses hydrogen as the coolant. Hydrogen was selected due to its high specific heat and suitability as a propellant. The authors used turbulent flow correlations and assumptions to estimate the heat transfer coefficient and convective heat flux along the nozzle wall. Their findings showed that the coolant temperature increased by only about 200 degrees Rankine, which indicates strong cooling capacity. The highest heat flux occurred at the throat, which is expected through isentropic flow relations and rocket nozzle theory. An important takeaway from this early work is that regenerative cooling alone may not always be as sufficient as you might need, and the author points out that combining it with film cooling or refractory coatings would likely yield optimal performance, and those refractory coatings are generally just heat-resistant paints. The second study we're going to look at focuses on a concern about using liquid oxygen as a coolant, namely whether cracks in the chamber walls could allow oxygen to leak into the combustion flow and create a safety or combustion stability issues. To investigate this, the researchers performed hot fire tests with initially pre-cracked chamber walls. They found that the introduction of oxygen through the cracks did not significantly impact thrust characteristic velocity or combustion stability. However, they did observe melting near the nozzle throat. So for follow-up tests, they revealed that the melting was caused not by oxygen leakage, but by injector design issues, which created localized oxygen-rich regions in the combustion flow. The study demonstrates that LOX can be used safely as a coolant, but also emphasizes the importance of proper injector design to avoid hotspots. And the 3 cases for the trials are shown below. And going through those cases, they were able to come to their conclusion about which variable was specifically creating the issues. The third study, which is probably the one I find the most interesting, relates to high aspect ratio cooling channels and general channel geometry optimization. So looking at the geometry, and specifically the aspect ratio, we look at how this affects thermal performance and the pressure drop. Using computational analysis and not real-world experimentation, the authors evaluated several channel shapes under the constraint that the local coolant area remained constant. The results show that high aspect ratio channels provide real benefits, primarily in the throat region, where heat flux is the highest. Elsewhere, the gains are minimal and come at the cost of increased pressure drop, so this would mean that your pumps would have to work harder, and this might not be optimal for your design. The optimal configuration they identified was a bifurcated high aspect ratio channel that reduced gas side wall temperature by about 20%, while only increasing pressure drops by around 9%. fourth study looks at the effect of adding fins to the interior of cooling channels. Using a validated 3D CFD model with supercritical hydrogen, the authors compared a smooth baseline channel to several fin configurations. Fins are helpful because they increase turbulence and improve coolant mixing. This helps eliminate thermal stratification. Among the designs tested, the fully fin channel achieved the best performance, reducing maximum wall temperature by approximately 14%, with a corresponding increase in pressure drop. Overall, the study shows that fin geometries can enhance heat transfer, but designers must still consider the added hydraulic losses, and from the design shown, case 3 yielded the best results. The fifth and final study that we're going to talk about is super interesting because it actually builds off of that previous study. So now that we know fins can be helpful for our cooling channel geometries, we can actually look at the fin shape themselves. So building off this idea, we explore pentagonal V-shaped ribs machined into the channel walls. Several chamfer angles were tested to understand how rib geometry affects heat transfer. The results were very encouraging, so the smallest chamfer angle produced the greatest improvement, which was a 5-degree angle. And this reduced the maximum wall temperature from roughly 975 Kelvin to about 733 Kelvin. While pressure drops increased by about 24%, the overall thermal hydraulic performance improved by over 50%. This work demonstrates that relatively small geometric modifications can significantly enhance regenerative cooling effectiveness. In conclusion, all 5 studies tend to reinforce the same theme. Improving heat transfer almost always introduces trade-offs in pressure losses, manufacturability, or just general system integration. Effective cooling design requires balancing these competing factors to achieve both thermal performance and practical feasibility. Here's a list of sources that I used. I really hope you were able to learn something, and I really enjoyed sharing what I learned. Thanks for watching.